Welcome to the Crazy Hat Chemist. Today we are going to do another pencil and paper worksheet. Today is stoichiometry worksheet number 1. All right, number of expectations here prior to starting this worksheet. Number 1, you have watched my video on the stoichiometry unit. The whole video series, that is, you have watched my videos on chemical reactions. You have watched my videos on nomenclature. You also are familiar with your ions and charges so that you can come up with chemical compounds, and you are familiar with this stoichiometry flow chart right over here. I'll zoom on out of there so you can get the entirety in there. I'm also assuming that you are familiar with this. And I'm also assuming that you have a periodic table, and specifically the periodic table that I'm using here, and that is this one right here. All right, fantastic. So we're going to get started on this worksheet, and let's see if we can hammer out these problems. Again, this is the Stoichiometry 1 worksheet, and I'm going to go in detailed stepwise fashion how to do each one of these problems. So let's give it a start. All right, so this first problem says, at STP conditions, how many liters of molecular oxygen are necessary to react with iron to produce 0.298 grams of ferric oxide? So the first thing that we need to do here is we need to write a balanced equation. So we're going to have molecular oxygen. Molecular oxygen is O2, because it's a diatomic molecule. What state of matter is molecular oxygen in? It's a gas. So I'm going to put that right there like that. Plus, and is necessary to react with iron. Iron is Fe. All right. Hopefully that's good. And iron is an element that is a monoatomic element. It is a metal, so therefore it's a solid at room temperature and pressure. So that's state of matter as a solid. And then it says to produce, that means that gives me my arrow, ferric oxide. Ferric is Fe3 plus. Oxide is a periodic trend charge of 2 minus. So just making sure that everybody's okay with that here. And there's oxygen. That halogens has a 1 minus charge. Oxide has a 2 minus charge. And right over here is iron. And it's actually 1, 2, 3, 4, 5 elements that have 2 plus and 3 plus charges, iron being one of them. And the IC is designating that it's the higher of the 2 charges. If it had an OUS ending, it would be the lower of the 2 charges. Okay. All right. Fantastic. So ferric oxide, so what we're going to do is we're going to take the absolute value of these 2 numbers. That's a 3 and a 2. I'm going to take these 2 numbers, flip the numbers and bring them down, and I'm going to get Fe2O3. The type of reaction of which this is a combination type of reaction. So I'm combining 2 or more things together to make one thing. I'm not looking at solubility rules to come up with the state of matter of this, and this is a solid. This is actually just rust. So if you're familiar with rust, this is rust. All right, now what we're going to do is we're going to balance this equation. So we're going to write stoichiometric coefficients in front of each of these formulas. It's probably easiest if we start off with the oxygens. There's 2 oxygens here on the reactant side, 3 on the product side, and the greatest common factor there would be 6. So I'm going to put 2 in front of the ferric oxide and a 3 in front of the molecular oxygen. That will give us 2 times 2, 4 irons on the product side, and I'm going to have a 4 coefficient in front of the iron on the product side. So now I have this equation balanced. So now what we're going to do is we are going to read the rest of the problem again and figure out what it is that we have numerically and what it is that we want. It says that we have 0.298 grams of ferric oxide. So that means that we have 0.298 grams of this product right here. And then it says at STP conditions, this is extremely important, STP. How many liters of molecular oxygen are necessary to react? So there's my molecular oxygen, and I am going to go from this number, units, and formula all the way over to this other reactant of molecular oxygen. Okay, so let's start off with our stoichiometry here on this problem. So we're going to start off with a number, units, and a formula. That number that we have is 0.298. The units are grams, and the formula is Fe2O3. That's for ferric oxide, Fe2O3. And we're going to do a number of stoichiometric steps here. All right, so now what we're going to do is whatever units here are in this numerator term, they must go down here in the denominator of the next term. So that's grams are in the numerator, grams must be in the denominator, and I'm also going to have the same formula. That is ferric oxide, Fe2O3. All right. And what is it that we can go to from grams? So I'm going to look at a portion of my flow chart here, and grams is right here at mass. So there's only one thing we can go to from mass, and that is moles. So what do we use for that conversion is the molar mass. So we're going to go from grams to moles. Moles now tells me what the units are in the numerator of this same term. So it's going to be moles of the same formula, that's Fe2O3. Okay, all right, let me straighten that up there a bit. And how many moles? How many moles? It's going to be 1 mole. Okay, so 1 mole is equal to the molar mass. So what we're going to do is we're going to pull out our periodic table, and we're going to use the molar mass for iron. That's 55.85. We're going to multiply that by 2. And then we're going to take the molar mass for oxygen, that's 16.00. We're going to multiply that by 3. We're going to sum up those numbers, and then we're going to round it to the fewest number of decimal places, which iron has 2 decimal places on my periodic table, and oxygen has 2 decimal places on my periodic table. So my answer will have 2 decimal places. So that's 159.70. So that is the rounded molar mass for ferric oxide. Okay. All right, now I'm not quite done, but the reason that I'm doing this is following my canceling units and formula. Now I have moles of ferric oxide. Well, really what I want is to get liters of the molecular oxygen. So I first need to convert the ferric oxide into molecular oxygen. So right here in the numerator, I have moles. I'm going to have moles in my denominator of my next term, my same formula, and that's Fe2O3. And then in my numerator, I'm going to have moles of whatever formula I want within this balanced equation. I could go to moles of iron if I want to, but I'm going to go to moles of oxygen. And so that formula is O2. The numbers of which are in front of the moles is the stoichiometric coefficients from the balanced equation. So this is Fe2O3, that is a 2, this is a 2, this is O2, that is a 3, this is a 3. Okay, and you should see that the moles of ferric oxide cancels out then at that point in time. All right, awesome. So we have one more step that we're going to do. This is actually called a mole ratio that I'm rectangle boxing out right here. This is a mole ratio. This is the only time in which you can actually change the formulas, and I'm using the stoichiometric coefficients from the balanced equation. All right, I have one more step that I'm going to do. And now that I have moles of O2, I'm going to have moles of O2 here down in the denominator. Right now I'm going to pull out my flow chart, and I have moles. I've used the mole ratio. I've gone back and forth over here, and now I have moles. So I'm going to go from moles, and I could go to molecules, which would be to the right. But I don't want to do that. I could go from moles to mass, and that would be going to the left on this flow chart. but the question is actually asking how many liters at STP. So at STP conditions, and it must be STP, 1 mole is equal to 22.414 liters. So I'm going to use that. 1 mole is equal to 22.414 liters, and that's O2. And again, you should see that the moles of the O2 cancels out. And now I'm left with the units and the formula of which I want. Okay. Clarification that I've seen many times before with students making an incorrect answer, and that would be this molar mass is not 2 times. So when we calculate the molar mass, we are only referring to this flow chart. 1 mole is equal to the molar mass. No matter what the stoichiometric coefficients are on the balanced equation, it's absolutely 1 mole is equal to the molar mass. Never 2 moles, never 3 moles. I never multiply the molar mass by, let's say, that 2. Okay. So, all right. So now what we're going to do is we're going to take our numerator numbers. That's 0.298 times 1 times 3 times 22.414 divided by 159.70 divided by 2 divided by 1. And the number that I get on this here is going to be, let's see, here we go, is 6.27 times 10 to the negative 2. The units are liters, and the formula is O2. So this is my number units formula that's rounded correctly. Okay, and just to make sure that we have rounded this correctly, this number here, leading zeros do not count. This is 3 significant figures. This is a definition, so this 1 in front of the 1 mole is an infinite number of significant figures. This has 5 significant figures for the ferric oxide. This is infinite number of significant figures, infinite number of significant figures in front of the coefficients of the balanced equation, infinite number of significant figures, and this number here, it's been rounded, but it has 5 significant figures. So the fewest number of significant figures was my initial number at 3, and that's why this number has 3 significant figures for the answer. I put it in exponential notation, although it's not necessary to have it in exponential notation, just left it that way. You could have it in decimal form, and that would be perfectly fine too. There's nothing wrong with that. All right. So let's move on to the second problem on this worksheet. And here we go. There's this one right here. So this next problem here, let's see if we can hammer this one out. It says we have if 3.24 grams of magnesium reacts with chromic oxide, how many grams of the elemental product is produced? Missed the word is there, but hopefully you got that. Okay, so the first thing that we need to do, just like on the last problem, is write a balanced equation. So we have magnesium, and that is Mg, and that is an element in its standard state, which is a metal, so that would be a solid, plus, and then we have chromic oxide. Chromic is Cr3 plus, oxide is a 2 minus. These are both periodic trend charges. And I'll just pull out that periodic table that I had before. And there is chromium, and the chromic has the 3 plus charge. There's the oxide, and that has the 2 minus charge. So I'm going to take the absolute value of these two numbers, take them and flip them and bring them down. I get Cr2O3. And that is going to be a solid. Okay, and then we get how many grams of elemental product is produced. So we first need to figure out what type of reaction this is. The type of reaction this is a single displacement or a single replacement type of reaction. Magnesium is a metal. So since magnesium is a metal, it will displace a metal. So that means it's going to displace the chromium. So now chromium is going to be by itself as an element on the product side, and that is going to be a solid. Then the magnesium and the oxygen are going to get together. So I'm going to have to look at my periodic table. and find magnesium. It is in group 2 and it has a 2+ periodic trend charge. And then oxide has a 2- charge. So I'm actually going to take magnesium that's a 2+, oxide that's a 2-. I'm going to take the absolute value of these two numbers, Mg2O2, and then I have to reduce this. That reduction would give me MgO as my final product. So that's MgO. It's also a solid. All right, so single displacement reaction. The metal displaces the cation or the metal. And now what I need to do is balance this. By the way, this is following a single displacement characteristics, and that is an element, a California, and an element and a California. Now we're going to balance this. So what we're going to do is we're going to start off with this chromium here. There's 2 chromiums here. So I'm going to put 2 in front of the chromium and that chromic oxide. And there's 3 oxygens here on the reactant side. There's 1 here. So I'm going to put a 3 in front of the magnesium oxide. And then that will require a 3 in front of this reactant magnesium oxide. All right, now that I got a balanced equation, now I'm going to go back to my question here and see what I got. It says if 3.24 grams of magnesium reacts. So I'm going to start off with that. 3.24 grams of magnesium reacts. Okay, so that's actually starting off with this magnesium at 3.24 grams. And then it says how many grams of elemental product. So which one of the products, these are the 2 products, which one of the 2 products is an element? That would be this one. So I need to go to the chromium. All right. All right, so following our canceling of units, and that's stoichiometry, that's what this is all about. This is grams, this must be grams here, this must be magnesium. And then I'm going to use my flow chart and find out what I need to do. So I have a mass, I am going to go to moles. How many moles? 1 mole. So this is 1 mole of magnesium. And then I am going to use the molar mass. Okay, so I'm going to look on my periodic table for magnesium and find the molar mass. That's 24.30. Okay, so 24.30 for the molar mass of magnesium. You should see that grams of magnesium cancels out. Now I'm going to have moles of magnesium here in the numerator. I'm going to have moles of magnesium here now in the denominator. That will allow me to cancel out the moles of magnesium. That's the whole purpose of canceling these out. Okay. Now, what do I want? I want the elemental product. I want the product that's an element. That's the chromium. So I'm going to have moles of chromium here. Then I'm going to use this is right here in this rectangular box is going to be a mole ratio. And you can see that this is the time that I'm changing formulas. It's the only time I can change formulas. And I'm going to use the stoichiometric coefficients in front of the balance equation. So I have 2 in front of the chromium. There's 2 in front of the chromium. And then 3 in front of the magnesium. That's 3 in front of the magnesium. And then it says grams of elemental product. So I need to push this one more step here to grams of elemental product. So this is moles of chromium. I'm going to have moles of chromium here down in the denominator. Okay. And from moles, I can go to mass. So from moles, I can go to mass in one step using the molar mass. So that's what I'm going to do. I'm going to have grams of chromium here, and this will be 1 in front of the mole. Okay, I'm going to find my periodic table, and I'm going to find chromium, and that is right here, and that is 52.00 grams for the molar mass of chromium. So that's 52.00 grams for that. All right, you should see now that the moles of chromium now cancels out. All right. So just to note again, just to make sure, this molar mass of magnesium is only what is on the periodic table. Okay, and what is on the periodic table is 24.30 for magnesium, right? 24.30 for magnesium. Okay, I have not multiplied that number by 3. It's just 24.30. Furthermore, this chromium, even though there's a 2 coefficient in front of it, I am only using the molar mass for chromium, and that's 52.00. I am not using any other number. All right. So we're going to look at significant figures. Since this is multiplication division, this has 3 significant figures here. This has an infinite number of significant figures. This is 4 significant figures. This is an infinite number of significant figures, infinite number of significant figures, infinite number of significant figures, and 4 significant figures. So the fewest number of significant figures I have in this problem is 3. So I'm going to plug all this into my calculator. I'm going to take 3.24 times 1 times 2 times 52.00 divided by 24.30 divided by 3 divided by 1. And I'm going to round that to 3 significant figures. And my final answer here will be 4.62 grams of chromium. And then that will be my final answer that I have. All right. Hopefully that's good for you. All right. All right, let's tackle number 3. Little swig of water first, and let's tackle number 3. So here's number 3. All right, so it says, how many grams of liquid product is produced with the complete combustion of propane? 2.3 grams of propane. So the formula for propane is C3H8. Propane is a gas. I don't know if you're familiar with that, but you have a propane canister maybe attached to your barbecue at home. Okay. All right. And so a combustion reaction requires molecular oxygen. That's a gas. There's an arrow, there's a delta because we need to push this reaction forward with a kick. And then the products of all complete combustion reactions is carbon dioxide, which is a gas, and then water, which we're going to call a liquid. Okay, and now what we need to do is balance this reaction. This is a combustion reaction. Combustion reactions are always balanced in a particular order. That particular order is as follows. We're going to do carbons first. There are 3 carbons here on the reactant side. I'm going to place 3 carbons on the product side in front of the carbon dioxide. There are 8 hydrogens on the reactant side, and there are 2 here on the product side, so this requires a 4 right there. The number of oxygens right here is 6. The number of oxygens right here is 4 with those coefficients of 3 and 4 respectively. I'm going to add those 2 numbers up. That gets me 10 oxygens on the product side. There are no oxygens here, so I'm going to multiply and give a 5 coefficient in front of the oxygen. Perfect. Okay, now I'm going to start off with 2.3 grams of propane. And it says, how many grams of liquid product? So I got 2 products, carbon dioxide and water. The one that's a liquid is my liquid product. And I'm looking for grams of that liquid product. All right. So what we're going to do is we're going to start off with our 2.3 grams of propane. Just like that. And so we have grams of propane. We're going to have grams of propane here in the denominator such that our units will cancel. And using our flow chart, we're going from mass to moles. How many moles? 1 mole. What is the conversion between mass and moles? The molar mass. So I am going to say moles of propane. How many moles? 1 mole. Okay, and then grams of propane is the molar mass of the propane. And so I'm going to take the molar mass of the carbon, which is 12.011. I'm going to multiply that by 3. Then I'm going to take the molar mass of hydrogen. I'm going to multiply that by 8. And then I am going to sum them up. Since my last operation is sum, that's addition, I'm going to have the fewest number of decimal places. Carbon, again, has 3. Hydrogen has 4. So I'm going to have the fewest number of decimal places, which would be 3. So that's 44.096. Okay. This will allow me to cancel out grams of the propane. Just a note to yourself, okay? This is one of the most common errors in these problems is you have all the setup correct, everything is done correctly, you plug it into your calculator correctly at the end, and then all of a sudden you get the wrong answer and you're wondering what happened? Why did I get the wrong answer? And the reason is because you miscalculated the molar mass. So I highly recommend that you recalculate the molar mass after you plug it in here, but you're going to use a whole number. So that is, you're going to take carbon and take 12, multiply it by 3, take hydrogen, multiply it by 8, sum them up, and you should get 44. And if that rounded whole number is close approximate to your molar mass that you rounded, then more than likely you have done it correctly. All right? All right. All right, so if moles of propane are in the numerator, then moles of propane need to be in the denominator so that you can cancel out the units and the formula, okay? And then I'm going to have moles of whatever formula I want in this equation. And what do I want in this equation? I want water, so that's H2O. Okay, and I'm going to use the stoichiometric coefficients from the balanced equation. In front of the propane here is an assumed 1. So that's 1 in front of the propane. In front of the water is a 4. So that's a 4 right there. Okay, I've already canceled out the units for the moles of the propane. We have one more step because we're going to go to mass of that liquid product. I've gone to the liquid product. Now I need to go to the mass of that liquid product. This is moles of water. I'm going to have moles of water right down here in the denominator. Okay, and then I am going to go from moles to mass. And I'm going to be using the molar mass. So I am going to say 1 mole is equal to the molar mass in grams of water. Okay, and so what we're going to do is we're going to look on a periodic table. We're going to find oxygen, that's 16.00, multiply that by 1. And then hydrogen, 1.0079, multiply that by 2. I'm going to round that summed answer to 2 decimal places because oxygen has 2 decimal places. So I'm going to have 18.02. All right, and then that will enable me to cancel out the moles of the water just like that. All right, now what we're going to do is we're going to plug this into our calculator. We're going to take 2.3 times 1 times 4 times 18.02 divided by 44.096 divided by 1 divided by 1. And then we're going to get an answer from that. We're going to look at significant figures. This has 2 significant figures, infinite number of significant figures, 5 significant figures, infinite, 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 and 4 significant figures. So the fewest number of significant figures I have in this problem is 2. So my rounded answer is going to be 3.8 grams of H2O. And that's my final answer. NUF, N-U-F, that is number, units, formula. That's number, rounded correctly. Units, formula. Every correct answer in chemistry will have the following: number, units, and a formula. So make sure that you include that. All right. So we're done with this page. We're going to do the next problem within this series here. So let me find that. And that is right here. All right. Next one. Number 4. So this is when it gets kind of spicy, and I like that. So here we go. So we have if 3.06 grams of ferric oxide and ferric, Fe3 plus, O2 minus, reacts with 4.29 grams of carbon monoxide. That's a binary nonmetal. What mass of iron metal, that's Fe, is produced? The other product is carbon dioxide, that's CO2. This is not a type of reaction we have studied, but you can balance it. So we're going to try that ferric oxide first. That's Fe2O3. 2O3. That is a solid. Plus the carbon monoxide. That is a gas. Hopefully you're familiar with that. And our products are iron, and that is a solid, and carbon dioxide, and that is most certainly a gas. Okay, this is a pretty difficult problem to solve for writing the reactants and products, but hopefully the words within the problem helped you on this. All right, so now what we need to do is balance it. So what we're going to do is we're going to take a look at this and say, oh golly, what do we need to do? We need to put a 2 in front of that iron, and we're going to place a 2 right there in front of that iron. And then one thing here, this is a very difficult balancing, okay? And you should see that of the underlined carbon monoxide and carbon dioxide, there's one carbon here and one carbon here. Being that there's one carbon on both of these, that means whatever number I have in front of carbon monoxide and whatever number I have in front of carbon dioxide must be the same number. So we're going to try ones. So if there's a 1 here and a 1 here, then now the carbons are balanced, but now we're going to check the oxygens. So if this were a 1, then I have 1 plus 3 oxygens, so 4 oxygens. And if this were a 1, then I have 2 oxygens. So 4 and 2, that's not balanced. I'm going to try the next number, which is a 2 and a 2. If there's a 2 here in front of the carbon monoxide, I would have 2 plus 3, that's 5 oxygens. And if I were to have a 2 in front here, that would be 4 oxygens. That's not balanced. If I were to place a 3 here in front of the carbon monoxide and a 3 in front of the carbon dioxide, I would have 3 oxygens plus 3, that's 6. And this is 3 times 2, that's 6. Aha, there we go. Now we're balanced. Okay. Next thing that we're going to do is we're going to write down what information is given within this problem. It says we have 3.06 grams of ferric oxide. So 3.06 grams of ferric oxide and 4.29 grams of carbon monoxide. Now, this should be like a red flag for you on this right now. And that red flag is when I have a number for both reactants, that means that this is a limiting reagent problem. So this is a limiting reagent problem, okay? So it says, what mass of iron metal is produced? So I am looking for the iron metal in terms of grams. So I'm going to have to take this numbered units formula, convert it to grams of iron. I'm going to have to take this numbered units formula and convert it to grams of iron. Okay, there are many different ways of solving limiting reagent problems. I'm just going to go over but one method here. Okay, so hopefully that's helpful. So we're going to start off with 3.06 grams of ferric oxide. And we're going to take this all the way to grams of iron. So if this is grams of ferric oxide, then I need grams of ferric oxide down here in the denominator. And from grams, there's only one thing you can go to, and that's moles. So this would be moles of Fe2O3. That is 1 mole. And then we're going to calculate the molar mass for ferric oxide. Actually, this is the second time on this worksheet that we have calculated the molar mass for ferric oxide. So it's 159.70. I know your calculator will give you 159.7, but it's actually 159.70 because iron has 2 decimal places and oxygen has 2 decimal places. All right, just a thought. We have moles of ferric oxide in this numerator, so we're going to have moles of ferric oxide in this denominator term. Then I'm going to use a mole ratio to go from moles of ferric oxide to moles of iron. And in this rectangular box, I'm using the stoichiometric coefficients from the balanced equation. So that is a 1 in front of the ferric oxide and a 2 in front of the iron. I'm ultimately trying to get to a mass, which is grams. So I'm going to take this one more step. Okay. And that is 1 mole of iron. And then the molar mass for iron on the periodic table, and that's 55.85 grams of Fe. Okay, and we should be looking at significant figures. This has 3 significant figures, an infinite number of significant figures, 5 significant figures, infinite number of significant figures, infinite number of significant figures, infinite number of significant figures, and 4 significant figures. So the fewest number of significant figures I have is 3. I'm canceling out my units and formula of grams of ferric oxide, moles of ferric oxide, moles of iron. And then I'm left with grams of iron. So I'm going to get a numeric value for this in my calculator. And that numeric value is 2.14 grams of Fe, that's iron. Okay, now I'm going to slide this up and we're going to do our next stoichiometric step. And that is starting with the 4.29 grams of carbon monoxide and taking that all the way to the grams of the iron here. So I'm going to take my 4.29 grams of carbon monoxide, and I'm going to do a similar stoichiometric setup as what we did previously. Okay, so I'm just going to slide this up so that you can see this here. That's 4.29. Okay, so this is grams of carbon monoxide. This will be grams of carbon monoxide. And I can go from grams to moles. That's the only thing I can go to. So that's moles of carbon monoxide, and that's 1 mole. And then I'm going to look at the molar mass for carbon monoxide. Oxygen has 2 decimal places. Carbon has 3. So this answer will be rounded to 2 decimal places. That's 28.01 for the molar mass of carbon monoxide. Canceling out moles of carbon monoxide. And then I want moles of whatever it is that I want, and that's iron. Okay, and so these are the stoichiometric coefficients from the balanced equation. So I'm going to pop up this balanced equation here again. Carbon monoxide has a 3, so this is going to be a 3. Iron has a 2, so this is going to be a 2. So in this rectangular box, it's the only time that I can change the formulas is with a mole ratio. Okay. One more step. I'm going to say moles of iron because this is moles of iron, and I'm going to go from moles to grams. So it's 1 mole of iron and 55.85 grams of Fe. And then that will be my ending part. I'm looking at significant figures, 3 significant figures, infinite number of significant figures, 4 significant figures, infinite number of significant figures, infinite number of significant figures, infinite number of significant figures, and 4 significant figures. So when I plug this into my calculator, I'm going to get 3 significant figures for my answer, and that will be 5.70 grams of Fe. So what I need to do is I need to compare this number and this number right here. Okay, so what I'm going to do is I am going to cross out the larger number. Cross out the larger number physically. That will help you not to sum these numbers up because that would be incorrect. So how much is the amount of iron that's produced? It's 2.14 grams of iron. So that's one of my answers. Okay, what is the limiting reagent? The limiting reagent is the one that made that. So the limiting reagent is ferric oxide. That's the limiting reagent. What is the reagent in excess? That is the carbon monoxide in excess. Okay, the one that produces or could have produced the larger number would be the one that's in excess. They always have to be reactants that you are looking at. All right. So now there's one more step here that we need to do, and that is we need to figure out how much carbon monoxide is in excess. So what we're going to do is we're going to take our limiting reagent and convert it to the one that's in excess. So that is, if I go to my balanced equation, I'm going to take the limiting reagent and convert it to the other reactant. It's that simple. And since we've done these two stoichiometric steps already, we already have calculated all the molar masses that we will need within this problem. So let's give it a try. So we're going to start off with our limiting reagent, which is 3.06 grams of ferric oxide. And I'm now going to convert this to the other reactant, that is carbon monoxide. So 159.70 grams of ferric oxide, and that's equal to 1 mole of ferric oxide. Then moles of ferric oxide is equal to moles of carbon monoxide. This is that mole ratio. That's the only time where you can change the formulas. Okay, and now I'm going to look at my balanced equation, and I am going to find the 1 in front of the ferric oxide and the 3 in front of the carbon monoxide and place those numbers where they belong here. 1 in front of the ferric oxide, 3 in front of the carbon monoxide. Then moles of carbon monoxide, and that will be 1. And then the molar mass for carbon monoxide. And again, we've already calculated that. So that's 28.01 grams of carbon monoxide. I'm going to do this math here. I'm canceling out units and formula, units and formula, units and formula. I'm looking at significant figures, 3 significant figures, infinite, 5, infinite, 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 and 4. And so the number that I get right here is 100, sorry, not 100, 1.61 grams of carbon monoxide. I'll write that down here for you. 1.61 grams of carbon monoxide. So this is the amount of carbon monoxide that is used or consumed or required. So how much carbon monoxide did I start with? 4.29 grams of carbon monoxide is what I started with. How much carbon monoxide did I use? 1.61 grams of carbon monoxide used. Consumed. What do we want to call it? I'm going to subtract these two, and then I'm going to get a numeric value. And that is 2.68 grams of carbon monoxide that is unreacted. This is my leftovers. Okay. All right. Hopefully that one looks pretty good. All right. So now we have one more problem to do, and that's our very last problem here of this worksheet. Here we go. And awesome. So we're going to take just a little station break here and say, well, golly, you are watching The Crazy Hat Chemist. Please watch my videos on YouTube. This is The Crazy Hat Chemist that you're watching here. Paper and pencil going to town here on stoichiometry problems. Please watch my videos on YouTube. I'd greatly appreciate that. If you find my videos on YouTube helpful, please subscribe, give me a like, give me a thumbs up. I greatly appreciate that. It really helps me out. Thinking like, hey, I'm doing a good job. I'm helping you out. So please help me out. All right. So now what we need to do is hammer on to our last and final problem here, number 5. All right. So hold on just a moment. All right, folks, let's see if we can knock this out of the park and finish this here. Here we go. We are on our last problem here. So we have 3.82 grams of aluminum hydroxide reacts with 10.25 grams of hydrochloric acid. If 1.47 grams of water is recovered, what is the percent yield for the reaction and how many grams of reactant remains unreacted? Oh my gosh, this problem is as good as it gets. And if you've watched my videos, then that phrase makes sense. This is like the last problem in the lecture, okay? And that is we are doing everything that we possibly can on this problem and for this unit, okay? This is an excellent problem. So we first need to get the aluminum hydroxide and the hydrochloric acid. So aluminum is a 3+, hydroxide is a 1-. So that is aluminum hydroxide, like this, okay? And then hydrochloric acid. So when it says hydroic acid, that is a binary nonmetal acid. Chlorine is the binary nonmetal, if you will. So that is hydrogen and a chloride like that, okay? And that would be HCl. This is going to be most certainly aqueous. This probably would be solid unless it says it's a solution because hydroxides are insoluble except for ammonium ion and a group 1s, of which that is not. This is a double displacement reaction. So I'm going to combine the aluminum with the chloride on the product side and get aluminum chloride. That is most certainly aqueous. And then I'm going to combine the hydrogen with the hydroxide, and that is going to be water. That's H2O, and that is a liquid. Now what we need to do is balance this double displacement reaction that we have here. And let's see, we have 3 chlorines and 1 chlorine, so we're going to place a 3 right there like that. And then now we have 3 oxygens and 3 oxygens, and now it's balanced. Fantastic. Okay, so many students have a hard time figuring out what to do with these types of problems. And what I recommend doing is write down the number with the formula that it's associated with, right with the balanced equation. So that's what we're going to do. 3.82 grams, and then 10.25 grams, and then 1.47 grams. Okay, so you should see that on this problem, like the last problem, when I have numbers for both reactants, it's a limiting reagent problem. When I have a number for a product, that is the product that I'm going to take both of these to. Why? Because I want a percent yield. This value right here is the actual or the given value in my percent yield. I need to calculate the theoretical value in my percent yield, okay? All right, so let's get moving on the stoichiometry portion of this problem and see if we can knock this here out of the park. So we're going to start off with our 3.82 grams of aluminum hydroxide. So 3.82 grams of aluminum hydroxide, like thus. And we're going to take this all the way to grams of water. Again, why grams of water is because I have a value for the water, and that way it will allow me to get a percent yield. So this is going to be grams of aluminum hydroxide down here in the denominator. And we are going to say that we have moles of aluminum hydroxide. This is 1 mole. This will be the molar mass. So I'm going to take the molar mass for aluminum, and we're going to get our periodic table that we're using here. We're going to take this value right here, 26.98, multiply it by 1, because there's 1 aluminum and aluminum hydroxide. And then we're going to take the oxygen, and we're going to multiply that by 3, because there's 3 oxygens in aluminum hydroxide. And then we're going to take the hydrogen and multiply that by 3, and We're going to sum these all up, and then we are going to round it to the fewest number of decimal places in aluminum, oxygen, and hydrogen, and that will be 2 decimal places. And my number is 78.00. Okay. That will now enable me to cancel out the grams of aluminum hydroxide. Now here down in the bottom, I'm going to have moles of aluminum hydroxide, and then moles of whatever it is that I want, which in this case is water. Again, I'm going to the water because I have the actual value for water and I want a percent yield. So I'm going to actually have to get this eventually anyway. I'm going to use the stoichiometric coefficients here. For water, it's a 3, and for the aluminum hydroxide, it's a 1. That enables me to cancel out the moles of aluminum hydroxide. I have one more step to get to the mass of water. Okay, so moles of water here in the numerator, moles of water here in the denominator. And then I'm going to have grams of water here in the numerator. And this is going to be 1 mole. I'm using my flow chart, and that is 1 mole is equal to the mass. What is it? The molar mass that it will be. Okay. And then in order to get the molar mass for water, okay, it's H2O. So I'm going to take oxygen and 1 times that, and then hydrogen and 2 times that, round it to the fewest number of decimal places, which is 2. So this will be 18.02. Okay. All right. Looking good so far. I'm going to look at significant figures. This is 3 significant figures. This is an infinite number of significant figures, 4 significant figures, infinite, 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 and 4 significant figures. So the fewest number of significant figures I have here is 3. So I'm going to take 3.82 times 1 times 3 times 18.02 divided by 1 divided by 1 divided by 78.00. And I'm going to round that answer to 3 significant figures. And the rounded answer is going to be 2.65 grams of H2O. That's my rounded answer here. Okay. All right. Now what we're going to do is we're going to deal with the other reactant, which is hydrochloric acid. So I'm going to start off with 10.25 grams of hydrochloric acid. Okay, so I'm going to scoot this baby on up here, and we're going to do another stoichiometric portion here. So that is 10.25 grams of HCl. And we're going to do a similar process that we did on the last one here. This is going to be grams of HCl down here in the denominator. From grams, I can go to only one thing, and that is moles of HCl. And that's going to be 1 mole. And then this is going to be the molar mass. So I'm going to take the mass of chlorine times 1. That has 3 decimals. The mass of hydrogen times 1. That has 4 decimals. My summed up answer will have 3 decimals, and that's going to be 36.461. Perfect. That enables me to cancel out grams of HCl. I have moles of HCl in the numerator, therefore moles of HCl will be in my denominator. Moles of whatever it is that I want to get to, and I want to get to moles of water. I'm going to use my stoichiometric coefficients from the balanced equation. So I'm going to double check on that for HCl and for water. And for HCl, it's a 3. For water, it's a 3. So that means that this is a 3 for the water and a 3 for the HCl. All right, cool. Now it's that enables me to cancel out moles of HCl. Moles of moles of H2O are in the numerator. Therefore, moles of H2O need to be in the denominator of the next term. And that will be 1 mole, and I'm trying to get to grams. So that's grams of H2O. And I already previously determined the molar mass for water. That's right up here, 18.02. So 18.02, so don't have to do that twice. I'm going to look at significant figures. This is 4 significant figures here. This is 5 significant figures. This is an infinite number of significant figures, infinite, 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 and 4 significant figures. So this number has 4 significant figures, but it really doesn't matter because this other one has 3. So I'm going to get a number in my calculator by taking 10.25 times 1 times 3 times 18.02 divided by 1 divided by 3 divided by 36.461. And I'm going to get the number of 5.07 grams of H2O. Okay. All right. Now, I'm going to compare these two numbers. Okay. So I can compare these two numbers. Why can I compare the two numbers? They have the same units of grams. They have the same formula of H2O. That's why I can compare the two numbers. Whereas before, at the very beginning of this problem, if you look up here, I have a number of 3.82 grams of aluminum hydroxide and a number of 10.25 grams of hydrochloric acid. Okay, I cannot compare these two numbers, even though they have the same units, they don't have the same formula. So I cannot compare these two numbers. I can compare these two numbers because they have the same units of grams, same formula of H2O. The bigger number, I'm going to physically cross out so I don't sum them up or do some crazy thing with it. So what is the mass of water that can be produced when mixing 3.82 grams of aluminum hydroxide and 10.25 grams of hydrochloric acid? The mass of water that can be produced is 2.65 grams of water. What is the limiting reagent? The limiting reagent is aluminum hydroxide. What is the formula in excess? Hydrochloric acid. So I'm going to write this here down just so that you understand it here. So 2.65 grams of the water. I'm picking that number because it's the smaller of the two. The one that made the smaller number is the limiting reagent. Okay. And the one that didn't make it is in excess. Okay. So I'm going to write this down. 2.65 grams H2O produced. AlOH3 is the limiting reagent, and HCl is in excess, kind of like the rock band, in excess. Okay, what we do need to do is do 2 more things, and that is get the percent yield and also get the unreacted reactant. We're going to do the percent yield first, since that's going to be actually a really simple, fast one. Okay, to get the percent yield, I'm going to take the actual value, which I mentioned before, 1.47 grams of H2O. That's the actual value because it's given in the problem. And I'm going to divide by the theoretical or calculated value, 2.65 grams H2O. I'm going to multiply this by 100. And then I'm going to get my percentage. My percentage is going to be 55.5% yield of water. Now, I want to make sure something is clear here. I'm going to take the actual. This value is given, divided by the theoretical. The actual is given in the problem. The theoretical is calculated. The number of significant figures is 3, 3, and infinite. So that's why this is 3. Okay. It's the small number over the big number. That's another way of looking at it. Okay, we got one more thing here to do on this problem, and then we're going to rock and roll here and say, check, done. All right, so the last thing that we're going to do is we're going to find out how much unreacted reactant remains. And that's the one that's in excess. So I want to figure out of the one that's in excess, the hydrochloric acid, how much of it remains unreacted. So what we're going to do is we're going to take our limiting reagent. Okay, our limiting reagent is a mass of 3.82 grams. And that limiting reagent is aluminum hydroxide. Okay, and I'm going to convert this aluminum hydroxide limiting reagent, the limiting reagent, into the one that's in excess. Okay, so I have all the numbers from the previous stoichiometric steps included in here already, so I just need to write them down. This is 78.00 grams of aluminum hydroxide. That's equal to 1 mole of aluminum hydroxide. I'm going to go from moles of aluminum hydroxide to moles of HCl. And so I'm looking at my stoichiometric coefficients on my balanced equation. That's 1 for the aluminum hydroxide, 3 for the HCl. That is 3 for the HCl and 1 for the aluminum hydroxide. And then I got one more step here, 1 mole of HCl, and then the molar mass for HCl, which is 36.461 grams HCl. When I do this, I'm canceling out grams of aluminum hydroxide, moles of aluminum hydroxide, moles of HCl, and I'm left with grams of HCl. I'm looking at significant figures, 3 significant figures, infinite, 4 significant figures, infinite, infinite, 5 significant figures, and infinite. So the fewest number of significant figures I have on this is 3. So I'm going to plug this in. I'm going to get a numeric value, and that's 5.36 grams HCl. This is the amount that is required. This is how much is required or how much is used. So in order to figure out how much is unused, what we're going to do is we're going to take the original amount of HCl. So the original amount of HCl is 10.25 grams of HCl. Okay, this is the amount that's available. Original, if you will. And I'm going to subtract the 5.36 grams of HCl that is required, consumed, or used. And then I'm going to get my final answer that I want on this problem. So I'm going to subtract these, and I'm going to get 4.89 grams HCl is unreacted. Again, that's 4.89 grams of HCl that is unreacted, available for another reaction if you wanted to. Hey, we just finished this awesome worksheet. I hope you really enjoyed the explanations. If you did, please subscribe to my YouTube channel. I am the Crazy Hat Chemist. Give me a thumbs up on this, please, if you would. I would greatly appreciate that. And tell all your friends, subscribe, thumbs up, comment. Thank you very much. Have a very good morning, evening, or afternoon. Talk to you later. Bye.